problems connected with your new position. I'm afraid I've been asking too much. And Sewell had just moved to Chicago, and he's in a new university. I mean, in the letters there are things about things going wrong with his apartment search or house search, and there's some very personal things going on in Sewell's life as he's has this big change. But Philip just couldn't resist, and he says, "My only excuse is that it is a mathematical problem which interests me very much, and which I thought you also might find not without interest." And he just knows that this close academic relationship continued and existed. They really solved it together in these letters. And Philip ends, and I think it's very meaningful, especially for everyone here who studies economics. He goes, "I hope all this work you have put into it is not going to prove obsolete. I hope you shall be able to see some results in practical application." So every time you use an instrument in your regression, just remember, it was two people who, independent of this economic economic aristocracy at the time, came up with this. And it's really the story of this collaboration between a father and son. And it's, I think, a very unique historical story, a very unique story in the history of economic thought. I'm so happy that the family's here today to kind of talk about it and learn about it. I'm so happy to have had these letters for my senior thesis, because it really is, it's really a magnificent story, and it's really a first really hard turn in the direction of the history of economic thoughts and econometrics towards something that was really, really meaningful at the time. Thank you.
Thank you so much. It was absolutely fascinating. And what I propose is that maybe we can have a few questions, maybe for Greenland and for from the audience. And people can also take this opportunity to eat some more food. We have a lot of food here. Don't waste it. And coffee. No leave. Don't take this opportunity to leave food. Somebody's locked the door. So questions from the audience. Yes. Yeah. You want to come and ask a question?
So I got the letters from, I learned about the letters from Professor Stock in a very in-depth way. So Professor Stock showed me this slide from his textbook, and when I first learned about instrumental variable regression and just like how to use it, he brings up this slide and says, this is a really interesting question, and I have a really interesting project for anyone who's interested in the history of economics and econometrics. And I jumped at it because I had done some work in it before. But he got the letters from Betty Rose right here. And I don't know, you said you found them. And she doesn't know where she found them, but it's really, it's good that you did find them, right? I wouldn't have a senior thesis. Thank you.
Other questions?
I can surmise why the paper was rejected, which we all can relate to. They just had some referees who couldn't understand their brilliant research.
There's actually a lot of reference to that in their letters. Sewell writes to him, you should have put my path analysis and stuff in the back. I think it was too far forward, and to be honest, the paper that they submitted, it still needs to be found. It's clearly what was intended to be. And also the rejection letter is, somehow Harvard lost it.
I'm curious, do you have access to, does the journal have files that go back that far? Is there a chance that if you don't find that, we'll find other rejection letters and be able to surmise more about grounds for rejection? Does Housing have letters in the archives?
Conveniently, the person who was in charge of applications started, who they have letters for, started sometime in the 1950s. They don't seem to have the knowledge of where those would be. It very well could be someplace in Harvard's archives, someplace else. But it's, I looked, I'll tell you, because that's the most interesting part of where they rejected it. I think it was just kind of seen as a, you know, we get tons of papers in every month. I don't think they realized they were rejecting like one of the most insightful papers probably they could have published. So.
So thank you very much again, and now we are moving to Professor Josh Angrist, who is the fourth professor at the Massachusetts Institute of Technology. He's one of the most creative and influential applied microeconomists, labor economists. He has done a lot of work in applied econometrics using instrumental variables in a very creative and original way that also opened the way to a lot of research by students and scholars in the past couple of decades, and he's also the author of a book that I believe is called Mostly Harmless Econometrics, which is a great book that I recommend. It's a page turner. If before going to bed, you can read Mostly Harmless Econometrics, an empiricist companion. So Professor Angrist is going to talk to us about contemporary uses of instrumental variables. His talk is called Instrumental Variables in Action. Sometimes you get what you need, which is encouraging.
It's a real wonderful experience for me to be here. What a pleasure to be in an event like this, given my interest in the instrumental variables, and of course, I know Jim's earlier study on the history very well, and I've really enjoyed learning about the insights of what's coming out of the letters, and I hope to look at them myself. I hope you guys will post them or something like that, maybe with some comments. Perhaps write a paper and dare the QGA to reject it. This time we'll keep the documentary record. So. I saw my job as, since Jim has done a wonderful job of explaining IV basics, I saw my job as linking some of Phillips Wright's contributions with modern econometric practice, which is in fact not as focused on simultaneous equations as economists were at the turn of the 20th century. The bigger problem, I would say the more common application today, is omitted variables bias. But so I want to talk about how we got to that and what the connection is. But let me start with a little bit of kind of disciplinary context. I know some of you are not economists and may wonder what's special about econometrics, so I'm going to say a few words about that as well. What's the difference between statistics and econometrics? Basically, statistics is concerned with the problem of statistical inference, how to go from a sample to a population. And this is, in fact, a fairly boring problem. And that's why I think statisticians do it. Econometrics is concerned with more fundamental issues, I think. A problem we call the identification problem. Identification is the problem of how to go from the relationships we observe. We completely ignore the inference step. We assume that the entire population is enumerated, so there's no statistical inference involved. And then we ask, can we go from the things that are measurable to the things that we really want to know? And the things that we really want to know are typically causal relationships. And the sort of classic example of a causal relationship in economics is a demand curve, which describes the causal effect of price on quantity demanded. And the reason of course, I do some inference myself, and some of my best friends are statisticians, so I don't want to poo-poo statistics too much, but the reason I think that identification is more interesting is that the identification problems are puzzles. They're puzzles, and so there's no sort of easy fix that's going to kind of mechanically work for all of them. The mother of all identification problems is the simultaneous equations problem or model. And this has been described many times. Jim showed how this works, and I thought I'd just flash it again very quickly. It's really never been described better than this. This is figure 4 from Appendix B, the tariff on animal and vegetable oils. And this shows the price quantity scatter plot and how the supply and demand curves really give you a cloud, which is not immediately informative about either relation. And then Philip has described how one curve moving with the other curve fixed. This is figure 3 from the appendix on the tariffs. The appendix to the tariffs, this describes how one curve shifting traces out the other. So here we have the demand curve tracing supply, and here we have the supply curve tracing demand. So you know, of course, you would see that graph today in any econometrics text, many economics texts as well. It's really a basic set of basic description of a classic problem that's stood the test of time. So where does a Wright fit in? How big is Appendix B? That's one way to think about it. I see Appendix B as essentially creating the Swiss Army knife of econometrics. It's the core idea around which all simultaneous equations, identification strategies, and here I'm talking about the ones that actually work as opposed to the ones on Jim's list, but the ones that came later that we understand today to be effective, like two-stage squares, indirect least squares, full information methods, various method of moments approaches. Everything is really built around those 2 pages in the appendix. But that's just for starters. It kind of boggles the mind for somebody that studies these problems to kind of dwell on this. IV also solves 2 other identification problems of major theoretical and practical significance. This came in the decades following Wright. I don't think Wright was thinking about these things, but he wouldn't be surprised. One is the problem of measurement error. That's a classic question. You want to relate y to x. X is measured with error. How can I fix that? That tends to impart bias to the measured relationship. That was solved first in a paper by Abraham Wall in 1940. That turns out to be IV, though it wasn't realized at the time. Jim Durbin later showed that. And the problem that's most of concern to me is emitted variables bias. You like to estimate the relationship, say, between wages and schooling. That's a classic example. Do people who are more educated, do they earn more because of that? Now, we'd like to control for all the things that potentially affect both schooling and wages. When we do that, it turns out that IV provides us a way to do that, even if we don't see all the things that we want to control for. So that's the omitted variables bias problem. I abbreviate OVB. So ME and OVB are also problems solved by IV, and those are actually probably more common applications today. If you open up the AER, say, or Econometrica, you'll see more of that use of IV than the simultaneous equations story. It's also interesting that progress here goes on. These problems, as big as they are, simultaneous equations, measurement error, OVB, that does not exhaust the power and the glory of IV. IV turns out to solve one of the most important problems in clinical research, which is the problem of partial compliance. So that's when you do a randomized trial and not everybody in the treatment group gets treated. There's a lot of self-selection into who follows protocol. That's a very important statistical problem. Howard Bloom was probably the first guy to figure out a simple solution for that. It turns out that that's IV as well. And I'll go through an example showing you that. Let me talk a little bit about how Wright's ideas have been interpreted in more modern work. The first step in any kind of identification analysis, particularly if you're talking about something where the relationship of interest involves causality, is to have a clear definition of what it means for a relationship to be causal. And Wright was very clear about this. I have to say, clearer than many of the people who were writing in the decades that followed. He had in mind the idea of an experiment, that causality is fundamentally related to the notion of an experiment. So he talks about elasticity. What is an elasticity? The economic concept of elasticity supposes different experiments with prices in the same market at a single instant of time. This is in the Appendix B. He defined causality very clearly in that way, but he also understood that it's a sort of a concept. It's a philosophical framework almost. It's not something that you can usually do. Obviously, such experiments cannot be made, he wrote. Actual observations must be made at different times and during the period between observations, conditions of both supply and demand may change. So he has in mind some sort of time series analysis. And he understands that it's confounded with shifting conditions besides the price changes that he would like to affect by an experiment. We've essentially adopted this notation in modern cross-sectional econometrics. We have slightly different looking symbols, but the idea is very much the same. We use a potential outcomes notation to describe alternative states of the world. We think of states of the world. You can think of a price as a version of this, but our sort of benchmark example is something that's either switched off or switched on, like a clinical intervention, so we call it a treatment. If treatment is switched on, you get to see one outcome. If treatment is switched off, you get to see the other. We call those Y1 and Y0. Now, what happens is we can use IV to analyze causal effects in that context. The effect of interest is the difference between Y1 and Y0. So an instrument allows us to capture features of that difference, not the difference at the individual level. For the same reason that this was difficult to write, it's difficult for us. But IV instruments give us some leverage on this problem when treatment is not randomly assigned in a real experiment. So here's just a version of the Wright story in the modern framework. Y0 has some randomness in it, so I'm going to denote that by the Greek letter eta. This is just the mean of Y0 there. The benchmark for modern econometrics is still constant effects, so we'll start with a constant effects story. Then we get something that looks like a regression. It's not really a regression, and the reason it's not a regression is that the treatment is not assumed here to be independently generated. That is, it's not independent of the randomness in Y0. And so if we just compare people who are treated and not treated, of course that's a simple difference in means. We get the difference in means, that's the observed thing. We'd like to learn about rho. We're not getting that though. And the reason we're not getting that is the Y0s of the groups that are and are not exposed to treatment are potentially different. Okay, let me make this a little bit more concrete. Big part of the debate over health insurance, national health care reform is the value of insurance, the health value of insurance. It is truly the case that people who have health insurance are healthier than people who don't. Is that because they are insured? Well, you might think so, but maybe not. They might have been healthier anyway, because the people who have health insurance differ in all sorts of ways from the people who don't. Those differences come into the modern notation as differences in Y0s, the health of somebody, even if they didn't have insurance. So anytime you see an observed relationship, you need to think about that, or you should think about that, I would say. The observed difference could reflect causality, but could also reflect differences in Y0. Here's another example. This is a classic. I think this is used in many medical schools to talk about selection bias. It's a classic example. People who served in World War II If we look at the birth cohorts that served in World War II, so that it would be primarily men born 1925 to 1928 in the United States, people who served in World War II lived longer than the people born in the same year who did not serve. Is that the benefit of military service? Is that the positive health effect of having served in the Army? Well, it's not impossible. You got some good things out of your service, undoubtedly, if you're a veteran. You're eligible, in fact, for cheaper health insurance later on. But it seems likely that that's confounded by selection bias. People who didn't serve in World War II were often not serving because they had relatively poor health, and they would have had poor health even in the absence of their service. Can we solve that problem? Well, the way to solve that problem is, in fact, my IV. So we look for an instrument that's correlated with service, but independent of Y0, not related to my intrinsic health, correlated with D, correlated with treatment, but independent of Y0. Applying the logic in Appendix B, page 314, we get exactly the formula that we saw earlier. It's a ratio of covariances. It looks sort of like a regression coefficient, but the covariances in this case involve the instrument and not the explanatory variable, at least not in the same way as regression. In fact, dividing both top and bottom by the variance, we see that the IV formula is the ratio of two regression coefficients. The first is the regression of the outcome, health or earnings, on the instrument, and the second is the regression of the treatment. In this case, I'm talking about military service, a dummy for having served in the military. Those pieces of the IV formula went on later. Probably this language came about in the 1950s. Today we call the pieces the reduced form and the first stage. I don't think Wright would have known what that meant. But those are exactly the top and bottom of his simple ratio formula. The reduced form is the effect of the instrument on the outcome. The first stage is the effect of the instrument on the treatment. Here's an empirical example from my own work. I asked whether serving in Vietnam, what are the effects of serving in the Vietnam era for men born in the 1950s on their earnings later in life? Did they get skills that raised their earnings, or were they kept out of the labor market and ended up earning less? So the outcome there, in my case, is earnings, could be health. This has been done also for health. The treatment is a dummy for having served in the Vietnam era in a sample of men born in 1950 to 52. Where do you get an instrument? Well, it turns out that President Nixon provided me with an instrument. I don't think this was his purpose in doing it, and we didn't really overlap. But he did transition from compulsory military service to voluntary, and part of that transition involved a lottery, a draft lottery, random numbers assigned to birthdays. Every birthday in the cohorts born 1950 to 52 got a random sequence number from 1 to 365, and men with low numbers were called first. Basically, there was a ceiling, and if your number was above the ceiling, you wouldn't be drafted. So, for example, men born in 1950 with numbers, that is, birthdays that had been assigned numbers below 195 were draft eligible. Everybody else was off the hook. So the instrument in that case can just be a dummy for having been draft eligible. And it turns out this works out very simply with a strong kind of finding. The draft eligibility reduced form on earnings in the 1980s, this is 15 years after the guys actually served, is about minus $400. That is, men who had low draft lottery numbers earn about $400 less than men who had high draft lottery numbers. Remember that low numbers make you eligible for service. The first stage, that is the effect of draft eligibility on the probability of service, is 0.16. So the ratio of those two numbers, that's this formula here, the ratio of those two numbers is the IV estimate, minus 400 divided by 0.6. It turns out that having been forced into the military in the Vietnam period reduces civilian earnings later on by $2,500, or about 15%. So that's quite a hit, and an interesting example of instrumental variables in action. Now, I haven't really gone through the whole spiel here telling you what it takes to believe this is the causal effect. We can talk about that a little bit. One way to understand this is to say, well, really what I'm assuming, one thing I'm assuming, this is relevance, Jim talked about it, draft eligibility affects the likelihood of service. Well, that's empirically fairly easy to check. The key assumption, and this is also floating around in Wright, in Appendix B is that the draft lottery number has no effect on my earnings through any channel other than increasing the likelihood that I serve. And in modern notation, that's like saying that the covariance of Y0 and Z is 0. Now, the modern framework develops from Wright in a number of ways, sort of picking up, we think, people who work in this framework, that's what I mean by we think we're sort of in the footsteps of that generation to some extent. One of the things we pick up on is the idea of causality tied to experiments. And so we think about our research, even when it's not experimental, we think of it as quasi-experimental or design-based, that implicitly there's always some kind of experiment. And we interpret our results in the hopes that that's credible. At the same time, once you become an experimentalist, you have to recognize that there's two types of validity in the world, and that's internal and external validity. A good instrument captures an internally valid causal effect. It identifies causal effects for people who are sort of in the experiment, whose behavior is immediately manipulable. So in the draft lottery case, we're learning about the effects of serving in Vietnam for people who were conscripted, not necessarily for volunteers, and of course we're not necessarily learning about World War II. External validity is the predictive value of those kind of estimates in other settings or other contexts. The modern framework highlights this distinction once you start thinking about a world of heterogeneous effects. It seems unavoidable to take that into account in interpreting your work. People like me, we focus mostly on internal validity. We emphasize that, primarily because I think that without internal validity, I'm not that interested in stories about external validity. I want to know that you've learned something about somebody, and then we can talk about the predictive value. So the draft lottery tells us about the effects of Vietnam-era military service. I might need a theory to understand whether that result applies to World War II veterans. I think it actually does, because I think that the reason that Vietnam veterans lost earnings is because they lost labor market experience, and that would apply to any generation of conscripts. In another study, Alan Kruger and I have used quarter of birth to estimate the returns to schooling. The reason your season of birth or your quarter of birth is an instrument for schooling is because the time of the year that you're born affects how likely you are to graduate high school. And this is sort of a consequence of compulsory attendance laws and the way that they're enforced in most American states. But since we can be forced to graduate high school, but not forced to go to college for the most part, the returns to schooling in that case are about high school graduation and not college graduates. That's fine. We get effects for a well-defined subpopulation, a subset of the treated, as it turns out. When the treatment, the variable that we're interested in, the causal variable of interest, has variable intensity, it's not just Bernoulli, but it's something like schooling that goes 0, 1, and 2. We typically learn only about a particular range. So in the schooling case, we're learning about high school graduation, but not college. Of course, we're very interested in the economic consequences of high school graduation, so that's not really a limitation, it's just something to think about. Here's an empirical example that I like to show when explaining this. I think this works a little bit better than some of the theory. This is from a paper of mine with Bill Evans. We asked a question that many labor economists have asked, which is, what are the economic consequences of childbearing? It's generally observed that women, men too, but especially mothers in larger families, earn less in bigger families. There seems to be a strong negative relationship between family size and earnings. Is that the price of childbearing? Well, it might be. It's potentially a causal story. I have kids, I don't work as much, I earn less. But it's also true that women who are less educated and have lower earnings potential might want to have more children anyway. It's the causality running the other direction. This has flavors of the simultaneous equations problem as well. So what we really would like to do when measuring the economic consequences of childbearing is randomly assign children to couples. That would be the ideal experiment. And I've been working for years on trying to get that experiment funded. And I'm hoping that giving this lecture will be helpful in that regard. But in the meantime, not being able to do that trial, that actual randomized trial, we look for an instrument. So the dependent variables in this case are measures of economic circumstances like work and hours and weeks worked and earnings. The treatment is a dummy. In this case, the treatment is a dummy for having a relatively large family among marital fertility. So a large family in the US is 3 children or more than 2. That's my parents' generation. I'm the oldest of 3. But in my generation, we have only 2. I have 2 children. And that's, in fact, what happened demographically, sort of between the 60s and the 80s. Completed family size fell from and I'm talking about marital fertility, fell from about 3 to about 2. At the same time, female labor force participation went way up, so that might be the causal link, okay? That could be why so many married women started working. I should say parenthetically, single women have always worked, but the big change in female work behavior is increased work by married women. So we need an instrument for that, and Bill Evans and I explored 2. We call the twins and same-sex instruments. The twins instrument we didn't invent, but we borrowed it from some econometricians, Mark Rosenzweig and Ken Wolpin, who used the event of a multiple birth as an experiment in family size. So, you're sort of rolling the dice, you're having that baby, and with probability about 0.01, about 1% of the time, you get a multiple. So that's like buy one, get one free. You have a bigger kid, a bigger family, and that's an experiment in family size that can be exploited to study the effects of family size on economic outcomes. Now I should say, this doesn't work anymore, so don't try it at home. For example, Carrie won't be able to use this for her thesis, but she doesn't need, she's got a great topic. Right? The reason twinning is no longer a good instrument is because now there's way, way more multiples. And that has to do with things like IVF and other fertility enhancements. So now you're going to have 3 times as many multiple births in the United States as we used to. But in older data, that wasn't a problem. So it's sort of like a rare event, and then bingo, you get an extra kid, and it's kind of like, God running a randomized trial with your family size. The other thing that we think works in this context is sibling sex preferences. That is, parental preferences over sibling sex composition. And what lies behind that is the fact that, well, in many countries, you may have heard about this, there's strong preferences for boys. So in South and East Asia, parents want boys. And so if they don't get a boy, they might be more likely to have another child until they do. It turns out Americans are not so interested in that. What really American parents want is a diversified sibling sex portfolio. So if they have 2 boys or 2 girls, they're much more likely to have a 3rd child. And that's essentially random. People think that there are things that they can do to affect the sex of their children, but barring sex-selective abortion, which wasn't very relevant in the period that I'm studying, there isn't much you can do. It's really a coin toss, about 50-50. It's really 0.51 that you have a boy. So the instruments in this case are either a dummy for a multiple or a dummy for a same-sex SIBSHIP. And in both cases, the formula is the same. It's exactly the Appendix B formula, the reduced form effect of the instrument divided by the first stage. In this case, there's a further simplification, and that's because the instruments are also in themselves treatments. The instrument is a Bernoulli, and so the reduced form becomes simply a difference in means, and the first stage is simply a difference in means. The reduced form for twins is the difference in labor force participation between mothers who do and don't have a multiple. The first stage for twins is the effect of twinning on the probability of having a 3rd child. The reduced form for sex composition is the difference in labor force participation or earnings between women who do and don't have a same-sex SIBSHIP. And the first stage is the effect of sex mix on family size. So here are the results of that. We can look quickly, we don't have to look at every number here. Let me start with twins. Here's the twins' first stage. Having a twin increases the probability of having a 3rd child by 0.6. Now that's a little puzzling at first. This is from a table in my paper with Evans. That's a little puzzling at first. You might wonder, How come I only got 0.6 of a kid when I had a multiple birth? So this is a good brain teaser when you teach econometrics, okay? How come you only get 0.6? Usually kids come in integer multiple. And the reason is that 40% of these women would have had a third child anyway. So twinning just pushes that 40% to a certainty. So the twins' first stage is 0.6. Here are the twins' reduced forms for a bunch of outcomes. Worked for pay, a woman who has a multiple, she's about 4.5 percentage points less likely to be working for pay. This is measured in 1980 census data. She works 2 weeks less, she works 2 hours per week less. These are all very precisely estimated relationships from a very large sample. She earns $571 less. So having a multiple reduces her earnings by $571. What does that mean that the causal effect of a child is? The causal effect of a child on her earnings is 571 divided by 0.6, which is 946, or almost 1,000.